Oh, no wonder. It's loading my wrong home directory. Alright, because I've got two things I want to talk about. Oops. Okay, so the two things I want to talk about today are um, some stuff that will be useful for the string to int and int to string type assignments, um, because we need to be able to do multiplication and division, um, which you can guys probably guess that integer multiplication and integer division are not that hard to do. But I want to talk through the details of it. So, all right, eject that and put it in here. And hopefully, how are you guys doing online this morning? All right, so twitch.tv moderator Prof McKinney. Mute the audio. So, Jack, hopefully you're doing all right. All right, so let's get to it. I need to, let's see, copy this stuff over. All right, well, so let's start with this. Integer multiplication and division. All right, so this will work a lot like integer addition or subtraction, um, which shouldn't come as a huge shock. Um, so, oops. So the ALU that's in this stuff in the processor, ALU stands for arithmetic and logic unit, right? So the thing that does all the math. And Mr. Vasquez, it is not that cold out there, bro. I'm sorry, my room was like -50 degrees. So. That is unlikely to be true. Uh, so, yeah, well, I was going to say January is going to be real fun for you. So, all right, well, so what do we got? The ARM ALU supports both 32 and 64-bit integer arithmetic, as we've seen, and it can do multiplication. Um, the syntax for this is basically just like it is for add, right, or subtract. Namely, you've got the two things that you're going to multiply are in registers XR and XS, and then the whatever the quotient or sorry product is, the destination register is XD is listed first. You can also do this with W registers instead of X's, but you can't mix them, right? So, yeah. Um, and this will compute the signed product of the two. So if the product is supposed to be negative, it'll be negative and so on, right? So it handles sign no problem. If you do mul with an S at the end, then that will also set the flags. I think we've seen that sort of stuff that you can do flag setting if necessary, which with multiplication is probably a good thing because if you've got two really big numbers and you multiply them, the odds of having an overflow are quite a bit higher than if you just were adding them or something, right? So, so if the flags are something that is important, then you certainly can do that. Um, Now, if we look at the documentation for this operation, what it says is that mul is really an alias of mad. Okay, so what is mad? This is where somebody's supposed to make a joke. Mothers Against Drunk Driving? No, it is a thing. I don't know. I guess maybe it's you guys are a little too young. They seem not to be as um, active as they used to be. But um, anyway, yeah. So, what is MAD? Well, just looking at the acronym, what would you think MAD has would mean? Hmm? So ideas. Jamba, you can't say anything because you know. No. So it's multiply add. Okay. Now you might ask, what the heck is that for? Well, let's move on. So this is what's called a fused multiply add. So the the multiplier object is capable of actually doing kind of two things at once. It does a product and an addition at the same time. So this particular operation takes four operands. Okay. The first one is, as usual, where the answer is going to go. The second and third one are the things that get multiplied, and the fourth one is the dude that will get added on at the end to the product. Okay, and we're going to talk about why on earth you would want such an operation. It seems like a really stupid idea um, to have this sort of mixed operation because uh, we could, if I did for some reason want to do product plus something, why not just do it as a product and then add the whatever as two operations? So why is it a good thing to have this in one operation? We'll talk about in a moment. Okay. Um, okay. So the syntax for this is a little bit annoying because of the order. So think of it this way, right? The first thing is always the destination. That we know we're pretty used to. The second and third things are the dudes that get multiplied, and then the thing at the end is the guy that gets added after the product has taken place. Okay, so of course, remember order of operations here. Well, let's see. Who are we missing? Shane, Owen, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so we're missing Shane and Owen and um, who's the fourth person that's missing? Third person that's missing? I'm blanking. Nah, whatever. Um, all right, so uh, now if you use mul in your assembly, then what the assembler is really going to do is replace mul with mad, but then the register that gets added on at the end, it just replaces that with the zero register, right? So if xt in my list there is zero, then I'm really just doing a straight multiplication and that's it, right? There's no, I'm just adding zero at the end, so nothing special. Gucci, has anybody got Shane's number? I was gonna say, why don't you blow up his phone? No. Hopefully he's online. Shane, if you're online, then say so in the Twitch chat. Jack is here. Yeah, like and subscribe. Well, yesterday morning I had to ban two bots for spamming in the text for like, click here to buy subscribers. Did I buy this? What do you think? I've All right, let's keep going. Yeah. All right. Well, all right. So why is this operation useful to have a fused multiply and add as opposed to just multiply and also add? Well, Couple things that this can be useful for. The first of them is that it actually will let us accelerate common operations. So let's suppose that you had a polynomial, and just for sake of example, I picked a real easy one. Let's just say I had x cubed plus x squared plus x plus 1, and I wanted to compute f of 3. Well, what would be the usual way that you would do this if you were in math class? We'd say, okay, well, 3 times 3 times 3 is 3 cubed, that's 27. 3 times 3 is 9. And so the answer should be 27 plus 9 plus 3 plus 1, and that gives us 40. Right? That's how you do it in math class. And that's perfectly good in math class. How many operations did this take? Well, it took us, what, 3 or 4 multiplications, depending on how you want to count, and 3 additions at the very end. We might have had to use some temporary storage depending on, how big the polynomial was, but it's not like this was that onerous in terms of arithmetic, but it probably took us what, like 7-ish operations to do, roughly. All right, so here's the smart way to do it. So I'm going to rewrite the polynomial like that. Now, first off, convince yourself that that actually is the same thing as 1 plus x squared plus x cubed. In fact, let me put this in opposite order here. It'll probably make it easier to read. Convince yourself that those two things are in fact the same. Yeah? Are we convinced? Okay, so notice it's nested parentheses, right? So in a sense, I've kind of done sort of recursive kind of view of this polynomial. I know it's maybe a little early for doing algebra when you guys just rolled out of bed, or didn't, Shane. He's going to be watching this video later and being like, okay, you guys convinced that they're the same polynomial? Yeah. All right, so how would I compute 3 plugged into that thing? Well, the first thing I do is 1 plus 3 times 1. Then I do 1 plus 3 times 4, which was the previous result. And then 1 plus 3 times 13, which was the second previous result. So I've sort of unwrapped this thing, or thought of it like in a recursive kind of way, and that only took me 3 fused multiply adds. Okay, so now, yes, I have done really probably, depending on how you want to count, 6 operations here, right? 3 products, 3 adds, but I've sort of grouped them using this hardware multiply add thing. All right, so does that kind of make sense? So let's see what happens if we do this in practice. So let me go over to here and let me copy these two over to my projects directory. And then pop open Genie. And let me close that. Close. And I want to open the MAD project. Oh crap. I forgot to copy the project file, but that's okay. All right, so we want projects, MAD. So I'm going to open 2 files. mad and nomad. Okay, so let me start with nomad, which is, so what I did was I wrote the same program, or a program to evaluate this polynomial at 3 twice. I wrote it once without the fused multiply add command, and once with it. Okay, and so now that's a little bit of a misnomer because the mul really is fuse multiply add, but I'm just not taking advantage of the add part at the end. Okay, so if I do this as two separate kind of things, well, first off, just to cover my butt, I'm going to put the result in x1. And so let me go ahead and make sure that x1 has 0 in it to start with, um, so that when I start adding and multiplying stuff, I'm not adding it to something that's already happened to be in x1. Um, okay. The numbers 3 and 1 were kind of important here, so I just load those two guys into registers 2 and 3. And then what I'm going to do is I'm going to compute, well, I need 3 squared and also 3 cubed, right, in order to deal with this. So I'll put 3 squared in x4 and 3 cubed in x5. Okay, so now I have 3 squared, 3 cubed, and 3 sitting in registers along with the ones. Okay, and then the sequence of add commands is really just saying, okay, well, it's 3 cubed plus 3 squared plus 3 plus 1, right, was my polynomial evaluated at 3. So do all that stuff, and then the reason I put all this in x1 is so that I could leave x0 free to put a memory address for a format string. Format string goes there, or address rather. Go to printf, so I can print out and see that in fact the answer is 40. Okay, great. So let's actually see this in action. So let me go into Le Terminal. And, oops. All right, so this is one sort of annoying thing about flash drives is that when you copy an executable to a flash drive and then copy it off the flash drive, uh, as a security precaution, Linux changes the permissions on it to make it not an executable file. So there's a way to change the permissions, but probably the easier thing is just reassemble it. Um, so, oh, sorry, we're doing Nomad first. I'm going to go ahead and statically compile this for reasons that'll become clear in a moment. Um, okay, and not shockingly, we get 40 as our output. Okay, wonderful. But what I want to think about is how long did it take to run this? Um, hmm, well, there's one way we can determine that, and that's to run this command. Okay, so that tells us, and let me do it a couple of times just for sake of demonstration, uh, tells us that it took, say, 3 milliseconds roughly to execute that program. Okay, great. Um, let's also, though, there's another thing I can do. Perf stat. Oh, blast. not installed. Let's see. Sudo apt-get Linux. Is it tools? I forget what it's. Oh, duh. All right, well, whatever. Forget that for now. So there is a thing called perf that will can actually tell us a lot more detail in terms of how long it takes for the thing to execute, but also how many cycles, machine cycles it took to execute. Now, when I ran this, so I wrote this code on my laptop, which is running Linux, but it's running x86 Linux, and then I'm emulating the ARM executable. So I can't use the perf thing because I would be measuring, I wouldn't be measuring just my code. I'd be measuring how fast it takes to run emulated code, which is not the same thing. Okay. So, all right, I'll figure out. It's like Linux Tools Common or Linux Common Tools or whatever. I don't remember what it. Oh, and no wonder I did the same thing twice. It's install. All right, let's see what it is. Let's just do Linux perf. Ah, I always forget the install part. Oh. All right, I'll let that run. Okay, but anyway, so this thing would tell us how long it, how many cycles it took to run, how long it takes, and so we get some kind of good data out of that. All right, so while that thing's running, let's go back to the, all right, so let's see if that, if this works, I'll post a list of instructions for you guys. This might take a minute. All right, so while that's working, let's just go back to this. So this may not seem all that good of a speed up when we're here, but imagine if we had a really big polynomial, okay? In particular, why might you want to be evaluating polynomials, like even if we were doing floating point stuff, which we'll start talking about next week? Math guys. Well, there's a special kind of polynomial that we talk about in calculus quite a bit. Huh? Named after a guy named Taylor. You know? Okay, so we could use Taylor polynomials to approximate things. For example, what would happen if I wanted to do trig functions if they're not built into my ALU? Huh? Mr. High, is this going to be a problem? No? To have some Taylor polynomials? Well, actually, it'll be even better because you know a better way to do it in certain instances? We'll have to talk about Chebyshev polynomials, which you guys have never heard of. Yeah. You've heard of them. Have you heard of Chebyshev polynomials? Yeah. Okay. Yeah. So anyway, when we get to the floating point stuff, I'm going to show you guys some pretty cool stuff. Um, how did I do this again? There we go. Yeah. So, okay. So, yeah, if we had a big polynomial in terms of degree, then I guarantee you this would speed things up quite a bit. And actually, if you think about it for a minute, if you had a really big polynomial, like this wouldn't work for, say, sine or cosine, but let's take the Taylor polynomial for, say, e to the x. Do you happen to remember what it is? 1 plus x squared over 2 plus x cubed over 3 factorial plus and so on, right? So if you have a polynomial, a big polynomial that has both odd and even powers, you can actually speed this up even more by doing the odd powers here, doing the even powers there, and then putting the two together at the end. So you can get a little bit of speed up there. But point being, what we're doing is sort of thinking about this in a recursive kind of way. And this is called Horner's rule. It also has a few other names because Horner wasn't the only guy to notice this sort of thing. So if you have a polynomial of the form a naught plus a1x plus a2x squared plus dot 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 plus a n x to the n, then you can sort of think about it, evaluating it in this recursive manner of a naught plus x times a1 plus x times a2 plus x times and so on, however deep you got to go. And that looks like a bunch of fused multiply adds to me. Um, and that's kind of nice. So um, I'm going to be a little loose here with the math, but how many operations is that? Well, if it's degree n, then we have to do n of these fused multiply add thingamajigs, which means it's big O of n. All right, now, how many of you guys have took algorithm analysis last semester? You took it. None of you? Okay, well, you'll get there, my friends. Well, actually, you guys are talking about big O and data structures, right? Yeah. So, so you guys know the difference between big O and of n versus big O of n squared, right? If you do this with the MAD type operation, then it's big O of n because you only have to do n of these things. Well, okay, I'm being a little slightly lying there because what else do you have to do? You have to load in all the coefficients, and that does require work. But because they're n coefficients, at most you would have to do n load operations. And so, but what do you know about big O? What's big O of 2n? That's really the same as big O of n, right? Because the coefficient part doesn't matter. Yes? Yeah, big O? Yeah, okay. Whereas if we did it the regular way, then we would have to do basically uh, a bunch of multiplications plus the additions at the end. And depending on how we store this data, if we do the multiplications like, if we're really stupid about it and we don't, like, let's say that we had 3 cubed, wouldn't it be smart to store 3 squared along the way as a temporary value? Yeah, because then I don't have to recompute 3 squared, right? But if I were really stupid and didn't, then this would be O n squared. Okay. So point being, Horner's rule can speed things up, and since, well, okay, so let me also be clear. there is no just straight multiply on these machines. If you do a multiply, you are really doing a fuse multiply add, but what are you adding? 0. Okay, so every time you do a quote regular multiplication, you really are doing a fuse multiply add, which is what means that I can compare these two things together, and it's an apples to apples comparison, not an apples to oranges comparison. Um, okay, so you can do some really nifty stuff with this rule. And if you guys want to make Dr. Turner really happy, go up and tell him the next time you see him that Horner's rule is the coolest thing ever, because he really likes Horner's rule. Okay. All right. Anyway, so yeah, you can be really fast with that. All right. There is also a variation of this called fused multiply subtract. Well, if we can add, we can subtract. Big shock. Um, and the syntax for this one's even more annoying because what we do is we're not subtracting something from the product, but rather we're subtracting the product from something. Okay, so the syntax is m sub xd xr xs xa, and that's what it computes. It multiplies xr and xs, subtracts the product from xa, and then puts the result in xd. Okay. Now, why might you want this particular operation? I mean, if we can add, we can subtract, right? That's not anything glorious. But where this is really handy is when you're doing modular arithmetic. So we'll talk about that in a second once you guys are ready to moveth on. Yes. Yes, Evan. Yeah. Not blind. Yeah. Because, well, all right, it depends on the language, but um, the division, the modulus, right, is really about the remainder, and the remainder upon dividing by 5 is the same as dividing by -5, right? So I would just I would just omit the negative. It doesn't matter. Right, because the remainder is 0. Right, right. Well, okay, now if you do that, so like let's say you divide it by 5 and you got remainder -1, that's the same as remainder 4, right? Because -1 and 4 are really the same thing in mod 5. Yeah, you should take more math. Okay. All right, so anyway, why would this operation be useful, or this version of it? Well, we'll get there in a moment. Well, if we can do multiplication, wouldn't it be nice to be able to do division? Yeah, probably. All right, so there are two operations that are defined, udiv and sdiv, and the difference is whether or not it's signed or unsigned. And what both of these things are going to do is they're going to take one register, divide it by another register, and divide them as integers, meaning that it's going to discard the remainder. Okay, so, if I did, for example, 5 divided by 2, I would get 2. It should be 2 remainder 1, but this is integer division, so that's it. Okay, so one warning here is in integer world, there is no way to encode plus infinity or error or anything like that. So if you are stupid and divide by 0, what's going to happen? Well, It won't. There's no way to encode that. In floating point there is, as we'll discuss next week, but with integers there's no way to encode the idea of error. Right? Because think about, if you've got, say, 64 bits to encode whatever, we use all 64 bits in an integer, right, to get minus whatever to whatever. Is there anything along the way that's allocated to just be error? Or let's really test y'all's trivia. I am error. No? That's what you would have to do, but you have to do that. Yeah, okay. So, yes. So, let me rephrase here. There is no built-in error checking in the hardware for you dividing by zero. If you want there to be error checking to prevent the user from doing that, you have to program it. Okay? It's not built in. Now, as we'll see with floating point, it's a little different in floating point world, but because there are actually encodings in IEEE 754 for plus and minus infinity and also not a number, which you can use as sort of an error or kind of thing. All right, so if you divide by zero, it's going to give you zero, which of course mathematically is bogus, but of all the integers that you could pick, which one would you pick? Well, zero is probably the most reasonable. So yes, to be smart, what you would have to do is have some sort of check. Hey, am I about to divide by zero? Because if so, I'm probably going to get completely erroneous math. Okay, so you have to be smarter than the user. Now, let me go back up here, right? If I did 5 divided by 2, well, Evan was just asking about the modulus operation, right? So in C and Java, it's the percent operator, right? So if I do 5% 2, I want to get the number 1 as the output because that's the remainder upon doing 5 divided by 2, right? So if I want the quotient, the division operation will give me that. If I want the remainder, there is no command to just give me the remainder. Or is there? Well, sort of. You have to be smart. It's actually 2 operations. So what we're going to do is do the division and then use the fuse, multiply, subtract right after it. Okay, so I'll use the 2 together. So here I chose to put 5 in x1 and 2 in x2, and then I'm going to do the unsigned division of 5 by 2, and that gives me 2, which I put in x3. Gucci? Okay. Yeah, Jack, minus 0 and 0 are the same thing in integer land. Not true in floating point, but we'll see that next week. Okay, so do the division, and so now the quotient I have sitting in x3. Well, if I've got the quotient and I knew what I was dividing by, then what I'm going to do is original number minus quotient times divisor, okay, which is the M sub operation. So what that's going to do is the product of x2 and x3 gets subtracted from x1, and so I do 5 minus 2, which was the divisor, times 2, which was the quotient. 5 minus 4 is 1, which was my remainder. Okay, so if I need the remainder, I can get it, but I have to do a second operation to get it, which is perhaps mildly annoying. Um, if memory serves, actually, on Intel, the division operation gives you both of them. So, like if you divide one thing by another, it puts the quotient in one register and the remainder in another register. Which I think it's like it puts the quotient in the C register and the remainder in the D register or something like that. But um, because in essence, well, classic Intel architecture, how many registers did you basically, general registers did you have? Like way back, you had four, A, B, C, and D. Um, and they got expanded and stuff later, but a lot of the operations still only use those four for backwards compatibility reasons, right? Which is why you can take code that was written for an 8086 back in the 70s, and I could probably run it on my laptop, which was produced this year. Pretty impressive. Huh? Yeah. Brand new laptop running code from the 70s. It's pretty cool, right? Uh, but on the other hand, it means that the x86 or modern x86 architecture is rather crufty, shall we say, because it's got to keep the baggage of backwards compatibility with it. Um, so actually, that maybe brings up good subject. So how many of you guys are super excited for either PS5s or Xbox Series X's? Are we all PC Master Race in here? Yeah. Okay. Well, you guys are computer science majors, so I suppose that yeah. Well, who's going to buy one or has pre-ordered one? Probably a good move. Also, we're in the middle of a pandemic, so spending $500 on something is probably not the brightest idea. Yeah. So I don't remember. Yeah. Yeah. One X. Ooh. It doesn't work that way. Yeah. No, it doesn't work that way. So the reason I bring up the Xbox or the PS whatever, right, is that this is always an issue when they release a new console is it going to be backwards compatible? Can you play PS4 games on the PS5? There, I think the answer is mostly yes. Can you play PS3 games on the PS5? I don't know, right? No, and there's a good reason for that. Well, what's the architecture of the PS5 and PS4 for that matter? Well, there's 64-bit, but what architectures? What processors are under the hood? Yeah, they're AMD machines, right? Ryzen or Ryzen, however you pronounce it, right? What about the PS3? Huh? It is not an Intel architecture or AMD, but same difference in that sense. Um, the PS3 used these really weird processors. It was the Cell processor, and it was kind of a pain in the butt to program for. Um, but you could do some really cool stuff if you were a wizard with it. Um, hmm? They did. Now, two series ago on Xbox, so I guess the Xbox 360, this would have been the second Xbox. That actually used IBM PowerPC stuff, which is kind of interesting because Apple switched away from the PowerPC architecture at basically exactly the time that Microsoft adopted it for the Xbox. And the reason that they chose it for the Xbox was it was powerful. The reason that Apple moved away from it was because it was too powerful, meaning it took up too much energy, which if you're building a console that's plugged in the whole time, doesn't really matter. But if you're trying to build a laptop that has a battery life of more than 30 minutes, right, you need powerful computing, but without all the energy. And so they switched over to Intel. Okay, now what are they doing? They're going to ARM, which is yet another reason why it was a good thing that I'm having you guys do ARM stuff here, because I think that's a lot of things are going to move that direction. Okay, so Switch, Nintendo Switch, ARM processor. Mm-hmm. Well, okay, I should clarify. It's an NVIDIA Tegra system on chip, but the processor cores are ARM cores. Um, okay, and every phone that's in this phone and tablet in this room has an ARM processor or ARM architecture in it. Now, Apple is a little bit of a exception to this. So what Apple does, they are a licensee for the ARM instruction set, not the ARM architecture. Okay, so what I mean, what's the difference here? If you license the ARM actual architecture, they will give you the schematics for how to fabricate the chip, okay, or how to include that chip in, uh, a chip that you're designing. You could say, okay, this part over here is the ARM core. I'm going to put my other things over here, but they will show you the lithography of actually how to make the chip. That implements the instruction set, right? Or you can license the instruction set and you can say, I'll figure out how to design the chip for that instruction set, but I'll make it myself. That's what Apple does, right? So they're starting with, I think, the A4 or maybe A5. All of those chips, it's ARM instruction set, but Apple is actually designing the physical layout of the chip, right? And if they're crafty with it, they can actually do better than, because I mean, it's Apple, right? They've got the smartest people in the world working for them, or some of them anyway. Okay, so, right. So anyway, point being, we don't have a separate operation to do modular arithmetic, and the division operation doesn't give us the remainder. So if we want it, we have to do these two things together. Do the division to get the quotient, and then using the quotient and the divisor, we of course knew what we divided into. We could do this difference, and that gives us the remainder, and bam, now we've got the remainder. Okay, so put the two together in the old Texas two-step. No? Yeah? Okay. All right. So let's do some demo with that. I never actually showed you guys the other one because I was busy installing perf. Let's see if it works. Damn it. I may have to reboot. Okay, whatever. Trust me, it's faster. Um, all right, so let's look at the code for the MAD version, right? So that's it, 3 MAD operations. Of course, I've got to load the registers with the things I need to do it. Um, in this case, one of the reasons I picked the polynomial 1 plus x squared plus, right, is that all the coefficients are 1. And that just simplified things a little bit because it meant I didn't have to do quite as much, um, loading of coefficients. Um, okay, but anyway, there we go, right? So same idea. You guys can clearly see that the code's a little shorter, right? Because I've only got, basically 3 arithmetic instructions as opposed to, what was it, 7 before? Yeah? X1 is where I'm going to put the answer. So it starts, yeah, x1 is going to start basically at 0, right? And I'm just putting the answer in x1 because I want to print it, and that's where it would have to go anyway to use printf. So I might as well put it there from the get-go, and then I don't have to move it. So I'm just trying to be efficient here. All right, well, so let's assemble it and time this one. Yep. Yes, because actually, I guess I didn't need that instruction. But let me put x1 there if that's what I meant. Um, it's not going to end up mattering in this case because my first operation would nuke whatever's in x1 anyway, right? But to do an apples to apples comparison, I used 3 move operations here in the other one, so I better use 3 there so that that part of the program doesn't uh, like if there's a difference in how long it takes to execute these, I don't want it to be because of those move parts. I want to see why the MAD instruction is really beneficial. Good. Okay, so let's assemble the other version. So okay, same output. That's good, right? That I didn't mess it up. But then if I do time, right? Um, it's basically the same here. Um, and that's not too big of a surprise, right? Because I was doing a pretty small polynomial, right? Now, if I could get the perf thing to work, then the cycle count would be interesting. I'll futz with that to get it working, and then show you guys later. Okay, Gucci or Prada? Gucci. All right. So now, why is having well, okay, you're going to have to use the MAD or actually, I guess the M sub operation to do modular arithmetic. And where are you really going to need that when you're doing? Well, what's the assignments that are on the pile right now? Right. So what are you guys working on today? Or I think for tonight was the string copy. All right. Well, what's after the string copy? 2 upper and 2 lower. When you guys get to the 2 upper and 2 lower, you'll see why I had you do string copy first. Okay, I'm trying to build you guys up, right? Um, so for 2 upper and 2 lower, you probably won't have to use this, but you're definitely going to have to use this with the int to string and string to int, right? Because let's say that I give you an integer and I ask you to do int to string. Well, you're going to have to know what each digit is, right? Well, how do you get the digits out? You have to divide by 10 and look at the remainder, right? Because can you just say extract the far right digit? Why not, Mr. High? Huh? Uh, bit for bit, right? Because all the data is stored in base 2 or hex, depending on how you want to think about it. But base 10 and base 2 are not the same thing, lamentably, right? So your modular arithmetic's not going to work. Well, sorry, the modular arithmetic will work, but you can't just say, oh, well, I'll look at the last hex digit, and that will tell me the divisor, or sorry, the digit. Well, the last hex digit is not the same as the last base 10 digit, is it? Ah, womp womp. Yeah. Okay, so that's where you're going to need this modular business. Okay, so let's see what's next. Um, demo time. No. Well, I'm going to be gentle with it on today. Okay. not right this instant. All right, so to understand recursion, you must first understand recursion. Right, Dr. Brown? Right? It's hilarious, right? Okay. All right, so how the heck is recursion work? What makes recursion recursion? It's a function that calls itself, right? So, what are good examples of this? Well, the factorial function, the Fibonacci numbers, the towers of Hanoi. Any other good examples? Huh? Computing powers. Oh, no, actually, yeah, you could do that. Um, other examples? No? You can do some searching and sorting algorithms recursively if you're depending on the methods, but hmm yeah, merge sort, quick sort, those sorts of things. See what I did there? You guys are a handful. All right, so let's use the factorial function as an example. So what is the factorial function? How is it defined? What's 5 factorial? 5 times, 4 times, 3 times, and so on, right? That would be a closed form way of writing it that's not recursive. What's the recursive way to think about it? Well, what's 1 factorial? Okay, base case. What's 2 factorial? 2 times 1 factorial. So what's n factorial? N times n minus 1 factorial. Okay? All right, so for demonstration here, what I thought I would do to keep this gentle this morning is, let me actually open this in Genie so it's a little easier to see. So it's a little easier to see. Oh, this is a tough crowd. All right, so I wrote this in C, okay, to start. And so we can think about why this is recursive. Okay, so first thing in C, right, I need to include my standard input-output stuff so I can print. I first have to define my factorial function, and I choose to define that as this. So what kind of number goes into factorial? An integer. What kind of number comes out of factorial? An integer, right? So that's why it's int fac int of n. And then, of course, n is going to be my local variable inside of the factorial function. And what is the base case here defined to be? 1, right? So 0 factorial and 1 factorial are both defined to be 1. Okay, the 0 factorial one we don't really need to worry about here, but let's just take 1 factorial is 1. Otherwise, what am I going to return? I'm going to return the number times factorial of n minus 1. And that's why it's recursive, because now it's going to call itself. Okay, good. All right. And then my main routine here is int main void. I just hard coded this just for cleanliness to say start with the number 5, initialize the answer to be 0, and then I'll say the answer is whatever fac of 5 is, and then print it and return to the OS. Okay, good? Right. So you guys did this sort of thing in Java plenty, I'm sure. And great. So if I compiled this and ran it, right, no shock what's going to happen. So I compiled it, but I compiled it to, Well, actually, you know what? Let me recompile it. Reason being, I used a cross compiler yesterday, and so this is the actual compiler on the hardware. All right, so what did I do? I had GCC spit out the assembly for it, right? So that we can look at, this is machine produced assembly, not hand produced assembly. That's fine. But let's look at how the recursive structure looks in this particular instance. Okay. So we've got a lot of stuff here, but let's find where sort of the money shot is, right? So I've got my main routine down there. Okay. All right, so what's going on there? Well, a bunch of things happening. What's happening there? Storing stuff to the stack, right? Okay. Then, all right, take the stack pointer, put in 29, whatever. I need the number 5. It's using W registers here because I just did int in my C, not long int. Okay. It does this twice. I don't know why. Whatever. And then it's branching and linking to factorial. Okay. And 5 is where register 0 is where the factorial function is expecting that input to be, right? So, and I think we talked about this parameter passing. Where do you expect your inputs and outputs to be from subroutines? Yeah, starting at 0, going up through x7 possibly, and if you need anything more than that, you need to use the stack. Okay. Um, okay, so anyway, so it branches to the factorial function. Whenever it's computed it, now the answer is sitting in W0, which it stores to the stack. It then loads it from the stack into W1. It could have just done a move operation there, but whatever. And then we need our address for the print string. We can branch to printf and then terminate the program. Okay, so this is all the main routine, nothing big surprise there. It's the factorial part that I want to look at. Okay, so the factorial part, actually what the compiler has done is sort of split that into 3 chunks, right? Because what's the first thing that we have to do um, in this situation? Well, if it's a recursive program and the function is calling itself, let's say that I'm now, I mean, this is kind of like Inception, right? I'm in main, I go into factorial, I've called factorial again. So let's say I'm 2 levels down. How do I know where to go back to in regular factorial? Well, what tells me where I go back to? What register tells me where I came from? The link register. Okay, but if I'm calling a function from within a function, then I need to store the previous link register to the stack so that when I come back up the chain, I can pull it off the stack and go back up in another step, right? So what that means then is that the subroutine also has to store the link register to the stack and also the stack pointer or previous value of the stack pointer. So this is why the subroutine also has this store pair thing like we did with our main routines. Okay, because we're expecting that the function's going to call itself. Similarly, on the back end, when I get ready to return from the function, what do I need to do to mirror this store pair? I better do a load pair at the end to compensate. okay? And if we dig down, then let's find that load pair. There it is right there in L3. Okay, so what the compiler has done here is kind of split this into several parts. Okay, so notice here the comparisons. It really only needed to do the comparison once, but again, this is compiler produced, so it's not hand assembled. Well, I need to check, do I have the number 1 or not? If I do, what's the answer? 1. If I don't, what do I do? Well, yeah, in this case, yeah, branch to .L2. Okay, so on not equal, meaning that I don't have the number 1, I'm going to do operations starting here. Okay, if I do have equal, then that means that the answer is 1. I can load W0 with 1, the answer, and then exit, which L3, you'll notice, is what is in L3 here? It's basically all the finishing up stuff, right? Pop X29 and X30 off the stack and return. We're done with that routine. Okay. So the meat of it happens here in L2. Oops, wrong keyboard. All right, so here's where the meat of it happens, right? Well, so what's going on? I need to take 1 away from, like, so if I did 5 factorial, right, I'm going to do take 1 away, that means puts 4 in W0, branch to fac, and then what comes out of the factorial function is in W0, I copy it to W1, okay, I'm going to pull something off the stack, and then I'm going to multiply them. Okay, does that make sense? Yeah? Evan, you don't look convinced. Is it just too early in the morning to be doing recursion? What time did you guys go to bed last night? Oh, why? Well, okay. Well, you got so there's an interesting. I think it's a Japanese word. Let's look it up because it actually is kind of apropos. Yeah, it's like revenge. Revenge. Um, there's a special word for it, and let's see if Google has it. Yes, revenge bedtime procrastination. Like there's a word that means that. And it's like you have little control over anything else in the world, so you're going to stay up late just to stick it to the world. To get homework done. Yeah. Oh. Then you were probably Snapchatting with girls or something. Uh-huh. Video games. Gets them every time. All right. Anyway, so let's go back to our code here, right? So what's the this is where the meat happens, right? Because what am I going to do? I'm going to take 1 away from my number, send it to factorial. When I come back from that, multiply it by the number before I subtracted. And then after I finish the mul operation, then I go directly to L3, right? Because it's immediately after. I don't have to branch to it because it's right there. Okay, so could we clean this thing up quite a bit? Oh, yeah, definitely. Okay, we could simplify this considerably in terms of the code, to make it a little bit more readable. But the advantage of doing this is that, well, at the touch of a button, me hitting the enter key, I have assembly, right, for the factorial function. Okay. There's a couple things here that are kind of inefficient. So, for example, how many bytes am I expanding my stack pointer by every time? How many do I really need to expand it by? Just 16, right? So I am kind of wasting space, if you will, by over expanding the stack every time. Um, the other thing is that you notice how the stack pointer offsets are 28 or whatever. I mean, it's trying to be a little smart with this. So, um, uh, I could have been maybe a little bit more efficient with my stack pointer or stack usage. The other thing is just for quicksies, I did ints rather than long ints. So this is all using the 32-bit stuff instead of 64-bit. But in that sense, same difference, right? With one exception, what's going to be the advantage, especially with the factorial function of doing things in 64-bit instead of 32? Well, the factorial function, how fast does it grow? Really fast, right? It puts the exponential function to shame. So like if I did 100 factorial, that's a really big number, right? If I tried to do 1,000 factorial, right? So the advantage of doing this in 64-bit as opposed to 32 is just that I have more room for bigger numbers in 64-bit than I do in 32, right? That's all. Okay. All right. So, by way of reminder, what are we doing on Thursday? Yes, we're going to do a lab day in the Ed Tech Center at the back of the library on the ground floor. Okay. So, what do you guys need to bring? Your Pi. What else do you need to bring? The power supply and the HDMI cable. Okay. Do you need to bring anything else? No. If you wish to bring your keyboard and mouse, you're certainly welcome to do it, but we can also just use the ones that are already there. Okay. So at minimum, you, preferably clothed, your Pi, your HDMI cable, and your, well, you can come naked, but you better have a mask on, right? Or I guess, right, from South Park last week, your chin diaper. You're right. So yeah, yeah. So we'll do that. And those of you guys who are online, so Jack and Noah, we'll just we'll we can always talk individually. So all right, see you guys on Thursday. And some of you owe me a lot of assignments. So some of you guys are about to get a rude awakening in the next day or two. See you guys later.